Thermodynamics is a branch of physical and chemical sciences that explains how thermal energy is changed to other forms of energy and the significance of thermal energy in matter and chemical reactions. The word thermodynamics is a combination of two Greek words, thermi, which means heat, and dynamis, which means force or power. It essentially refers to the dynamics or movement of heat and how it interacts with various forms of energy and matter. The word thermodynamic was first used by Lord Kelvin in 1849. So what exactly is the thermodynamics in simple words? Thermodynamics is a study of relations between four important components of physical and chemical process. They are heat, work, temperature, energy, and how the transformation of energy within the system can take place and its capability to perform work in its environment. The concept behind the theory of thermodynamics can be well explained using a model of system and surroundings. What is a system? System is the part of the universe that we are focusing on or studying. It can be anything from a single atom to a large object like a car. In the diagram, chemical reactant in a jar is a system. What is surroundings? Everything else outside the system that can interact with it. This includes the environment around the system. In the diagram, air outside the jar is surroundings. What is the boundary? Boundary separates the system from surroundings. In the diagram, the jar is the boundary. As an example, if a cup of coffee is placed in a room, coffee is the system, cup is the boundary, and environment in the room is the surroundings. In thermodynamics, a system can be classified into any one of the three categories: open system, closed system, and isolated system. In the open system, exchange of heat energy and matter can take place between system and its surroundings. In the diagram, the cooking pot absorbs heat energy and transfers it to material inside, and some material can exit the pot in the form of steam. In a closed system, exchange of energy can take place but no exchange of matter between system and its surroundings. In the diagram, exchange of heat energy can take place between helium gas and the environment outside, but air cannot enter inside the piston and cylinder assembly. An isolated system, there is no exchange of heat energy and matter between system and its surroundings. In the diagram, hot water inside a thermos flask cannot exchange heat energy with its surroundings. The lid of the flask is also closed, so no additional matter can enter the flask. Every system in the universe has its own properties. In thermodynamics, the properties are broadly classified into intensive and extensive properties. Intensive properties are those properties that do not depend on the amount of matter or the size of the system. These properties remain the same regardless of how much substance is present. For example, temperature. Whether you have a cup of water or a swimming pool, if the temperature is 25 degrees Celsius, it remains 25 degrees Celsius. Pressure. The pressure inside a tire is the same whether the tire is on a bicycle or a truck. Density. The density of gold is the same whether you have a small ring or a large bar. Extensive properties are those properties that depend on the amount of matter or the size of the system. These properties change when the size of the system changes. For example, mass. The mass of a substance increases if you have more of it. For example, a ring of 10 grams versus a bar of 300 grams. Volume. The volume of a system increases with the amount. For example, 100 ml of water versus 1000 ml of water. The state variables are properties that describe the state of a system at a given moment. State properties help us understand the condition of the system without needing to know its history. Common state variables are temperature, pressure, volume, etc. State functions are properties that depend only on the current state of the system. not on how the system reached that state. This means their values are determined solely by the state variables. Examples of state functions include enthalpy, entropy, internal energy, etc. As an example, temperature and pressure in a gas cylinder. State variables are the temperature and pressure of the gas. State functions are the internal energy of the gas, which depends only on its temperature and pressure, not on how it was heated or compressed. Another example is water in a thermos. State variables are temperature and volume of the water. State functions are the enthalpy of the water, which depends only on its temperature and volume, not on how it was poured or heated. In thermodynamics, there are several types of processes that describe how a system changes from one state to another. They are isothermal process, adiabatic process, isochoric process, isobaric process, cyclic process, and polytropic process. In isothermal process, the temperature of the system remains constant. As an example, melting ice at 0 degrees Celsius, the temperature stays the same while the ice melts. In adiabatic process, there is no heat exchange between the system and its surroundings. For example, rapid compression or expansion of gas in an insulated cylinder where no heat enters or leaves the system. In isochoric process, the volume of the system remains constant. As an example, heating a gas in a sealed rigid container, the volume does not change but the pressure and temperature do. In isobaric process, the pressure of the system remains constant throughout. For example, boiling water in an open pot, the pressure remains constant at atmospheric pressure while the temperature and volume change. In cyclic process, the system returns to its initial state after undergoing a series of processes. For example, the operation of a heat engine, while that working substances goes through a cycle of process and returns to its starting state. Thermal equilibrium is a state where two or more systems in contact with each other do not exchange heat. This means that they are at the same temperature and there is no net flow of thermal energy between them. Examples are cup of coffee in a room. System is a hot cup of coffee. The air in the room is its surroundings. The process is initially the coffee is hotter than the room air, so heat flows from the coffee to the air. Eventually, the coffee cools down to the same temperature as the room air, reaching thermal equilibrium. Another example is ice cube in water. System is an ice cube placed in a glass of water. Water in the glass is its surroundings. Process is the ice cube absorbs heat from the water, causing the ice to melt and the water to cool down. When the temperature of the melted ice and the water equalize, they are in thermal equilibrium. One more example is thermometer in a liquid. System is a thermometer placed in a liquid. Surroundings is the liquid. Process is the thermometer measures the temperature of the liquid. When the thermometer and the liquid are at the same temperature, they are in thermal equilibrium and the thermometer gives an accurate reading. The first law of thermodynamics states that energy cannot be created or destroyed. It can only be transferred or changed from one form to another. In mathematical terms, it is often written as delta U equal to Q minus W, where delta U is the change in internal energy of the system, Q is the heat added to the system, W is the work done by the system. As an example, consider boiling water. System is water in a pot. The process is when you heat the water, you add heat energy to it. As a result, the internal energy of water increases, causing it to boil and turn into steam. Another example is a car engine. System is an engine of a car. The process is the fuel burns in the engine, converting chemical energy into heat and work. The outcome is the heat energy increases the internal energy of the gases. which then do the work by moving the piston, propelling the car forward. The second law of thermodynamics states that the total entropy of an isolated system can never decrease over time. Entropy is a measure of disorder or randomness. In simple words, natural processes tend to move towards a state of greater disorder or randomness. What does that mean? Imagine you have a clean, organized room. Over time, without any effort to keep it tidy, the room will naturally become messier. This increases the disorder is similar to how entropy works in thermodynamics. Melting ice. System is ice melting into water. Process is, as ice melts, the structured arrangement of water molecules in the solid state becomes more disordered in the liquid state. Outcome is the entropy increases because the liquid state is more disordered than the solid state. Mixing milk in a coffee. System is coffee and milk. Process is when you pour milk into coffee, the milk molecules spread out and mix with the coffee molecules. Outcome is the mixture becomes more uniform and disordered, increasing the entropy. Heat transfer. System is a hot object and a cold object in contact. Process is heat flows from the hot object to the cold object. Outcome is the temperature difference decreases, leading to a more uniform temperature distribution and increase the entropy. The third law of thermodynamics is a bit more abstract than the first two, but let us break it down in simple terms. It states that as the temperature of a system approaches absolute zero, that is 0 Kelvin or minus 273 degrees Celsius, the entropy of a perfect crystal, which is a measure of disorder, approaches zero. Imagine you have a perfectly ordered crystal where every atom is in its exact place. As you cool this crystal down to absolute zero, the atoms stop moving entirely. At this point, there is no disorder because everything is perfectly arranged and stationary. Therefore, the entropy which measures disorder is zero. Zeroth law of thermodynamics states that if two systems are in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. As an example, imagine you have two thermometers that are placed in the water bath. If the water bath is in thermal equilibrium with both thermometers, then the thermometers must be in thermal equilibrium with each other, meaning they should read the same temperature. Enthalpy is a concept in thermodynamics that represents the total heat content of the system. It is a measure of the energy in a system, including both the internal energy and the energy required to make space for the system by displacing its surroundings. Mathematically, it is represented as H equal to U plus PV, where H is the enthalpy, U is the internal energy, P is the pressure, and V is the volume. In the diagram, when heat is supplied to the gas inside the cylinder, it absorbs heat energy that causes the enthalpy of the gas to increase. As a result, the pressure inside the cylinder increases, causing the piston to move upward that will increase its volume. The change in enthalpy results in change in internal energy and the product of pressure and volume. Enthalpy is typically measured in units of energy per mole, such as joules per mole in SI units or calories per mole in calorie-based system. What is change in enthalpy? As we know, enthalpy is a state function. That means it is dependent on the initial and the final state of the process, not the path taken by the process. The internal energy, pressure, and volume are state variables. The change in enthalpy is represented by delta H and is given by the formula delta H equal to H2 minus H1, where H1 is the initial state enthalpy of system, H2 is the final state enthalpy of system. As we know, the formula for enthalpy is H equal to U plus PV. Then we can write H1 equal to U1 plus P1 V1, H2 equal to U2 plus P2 V2. Using the values of H1 and H2, the value of delta H will be delta H equal to U2 plus P2 V2 minus U1 plus P1 V1. That is delta H equal to delta U plus delta times PV, where delta U is the change in the internal energy, delta PV is the change in product of pressure and volume. In isobaric process, the pressure remains constant before and after state change. At a constant pressure P1 equal to P2 equal to P, delta H equal to delta U plus P times delta V. When the pressure inside and outside are the same, then the formula for the isobaric process will be Qp equal to delta U plus P times delta V. Thus, from the above two equations, we get delta H equal to Qp. Thus, from this derived formula, we understand that the increase in enthalpy of a system is equal to the heat absorbed by it at a constant pressure. For reactions between solids and liquids, change in volume and pressure are negligible and we can consider them to be zero. Therefore, delta of PV equal to 0. Therefore, delta H equal to delta U. However, for reactions involving gases which are easily affected by change in pressure, delta V should strictly be considered. If we assume that temperature remains constant in the process, delta H equal to delta U plus delta times PV. Therefore, delta H equal delta U plus delta times P2 V2 minus P1 V1. If N1 equals moles of gaseous reactants and N2 equals moles of gaseous products, using the ideal gas equation PV equal to nRT, at constant temperature delta H equal to delta U plus N2 times R2 minus N1 times RT, which means delta H equal to delta U plus RT times delta N. Enthalpy of fusion. Enthalpy of fusion is the amount of heat energy required to convert a unit mass of a solid at its melting point into a liquid form without an increase in temperature. As an example, enthalpy of fusion of ice equals 334 joules per gram. This means that it requires 334 joules of heat energy to convert ice into water at its melting temperature. Enthalpy of vaporization. Enthalpy of vaporization is the amount of heat energy required to convert a unit mass of a liquid at its boiling point into vapor state without an increase in temperature. As an example, enthalpy of vaporization of water equal to 40.65 kJ per mole. This means that it requires 40.65 kilojoules of heat required to convert 1 mole of water into steam at its boiling temperature. Ionization enthalpy. Ionization enthalpy of an element is defined as the amount of energy required to remove an electron from the isolated gas in its gaseous state. Ionization energy depends on the force of attraction of electrons and the nucleus. Activation enthalpy. This is the minimum energy required for a chemical reaction to occur. One classic example is the decomposition of hydrogen peroxide into water and oxygen. It requires heat energy of 75 kilojoules to decompose 1 mole of hydrogen peroxide. Now we shall solve some relevant exercises to have better understanding of the subject. Exercise 1. For a reaction, the system absorbs 10 kilojoules of heat and does 3 kilojoules of work on its surroundings. What are the changes in the internal energy and enthalpy of the system? According to the first law of thermodynamics, delta U equal to Q plus W, where Q equal to plus 10 kilojoules and W equal to minus 3 kilojoules. Q equal to plus 10 kilojoules, it is positive because the system has absorbed heat energy. W equal to minus 3 kilojoules, it is negative because the work is done on the surroundings by the system, so the system has lost that energy. Therefore, delta U equal to 10 kilojoules minus 3 kilojoules, which is equal to plus 7 kilojoules. Delta H equal to delta U plus delta times PV. Here delta times PV equal to work done by the system, which is equal to 3 kilojoules. Therefore, delta H equal to plus 7 kilojoules plus 3 kilojoules equal to 10 kilojoules. Thus, the internal energy increases by 7 kilojoules and the enthalpy by 10 kilojoules. Exercise 2. An ideal gas expands from a volume of 5 decimeter cube to 15 decimeter cube against a constant external pressure of 3.036 10 to the power 5 Newton per meter square. Find delta H if delta U is 400 joules. Given gas expands at constant pressure, which is equal to 3.036 10 to the power 5 Newton per meter square. Change in internal energy equal to delta U equal to 400 joules. V1 equal to 5 decimeter cube equal to 5 to 10 to the power minus 3 meter cube, and V2 equal to 15 decimeter cube equal to 15 into 10 to the power minus 3 meter cube. Change in enthalpy equals change in internal energy plus P times delta V. Therefore, delta H equal to delta U plus P times delta V. Substituting the values in the equation, we'll get delta H equal to 400 joules plus 3.036 into 10 to the power 3 joules. Therefore, delta H equal to 3436 joules. Exercise 3. Calculate the work done in the following reaction when 2 moles of HCl are used at constant pressure at 420 Kelvin. The reaction is 4HCl, which is in gaseous state, plus O2, which is also in gaseous state, gives 2Cl2 in gaseous state plus 2H2O in gaseous state. State whether the work done is by the system or on the system. Given 2 moles of HCl react with 0.5 mole of oxygen to give 1 mole of Cl2 and 1 mole of H2O. Hence, N1 equal to 2.5, N2 equal to 2, R equal to 8.314 joules per Kelvin per mole, and T equal to 420 K. According to the formula to calculate the work done in chemical reactions, W equal to minus delta N times RT. Therefore, minus RT into N2 minus N1, which is equal to W. Substituting the values in the equation, W equal to minus 8.314 multiplied by 420 multiplied by 2 minus 2.5, which is equal to 1745.94 joules. Work is positive, so work done is by the system. Exercise 4. Calculate the change in enthalpy delta H for the combustion of methane CH4 if the standard enthalpy of formation of methane is minus 74.8 kilojoule per mole. The combustion reaction of methane is CH4 plus 2O2 gives CO2 plus 2H2O. The standard enthalpy of formation of CO2 is minus 393.5 kilojoules per mole, and the standard enthalpy of the formation of H2O is minus 285.8 kilojoule per mole. To calculate the delta H for the combustion of methane, we need to use the standard enthalpy of formation of the reactants and the products. The delta H can be calculated using the formula delta H equal to sum of N times delta H F of products minus sum of N times delta HF of reactants, where N is the stoichiometric coefficient of each species in the balanced chemical equation. Delta H equal to 1 into minus 393.5 kilojoule per mole plus 2 into minus 285.8 kilojoules per mole minus 1 into minus 74.8 kilojoules per mole plus 2 into 0 times kilojoule per mole, which gives delta H equal to minus 727.4 kilojoules per mole. Therefore, change in enthalpy for the combustion of methane is minus 727.4 kilojoules per mole. Exercise 5. In a process, 701 joules of heat is absorbed by a system and 394 joules of work is done by the system. What is the change in internal energy for the process? According to the first law of thermodynamics, delta U equal to Q plus W, where delta U equal to change in internal energy for a process, Q equal to heat, W equal to work. Given Q equal to plus 701 joules since heat is absorbed, W equal to minus 394 joules since work is done by the system. Substituting the values in the expression, we get delta U equal to 701 minus 394, which is equal to 307 joules. Hence, the change in internal energy for the given process is 307 joules. Exercise 6. The reaction of cyanamide NH2Cl with the dioxygen was carried out in a bomb calorimeter and delta U was found to be minus 742.7 kilojoules per mole at 298 Kelvin. Calculate enthalpy change for the reaction at 298 Kelvin. The reaction is NH2Cl plus 3 by 2 O2, which gives rise to N2 plus CO2 plus H2O. The solution is enthalpy change for a reaction delta H is given by the expression delta H equal to delta U plus delta NGRT, where delta U equal to change in internal energy, delta Ng is a change in number of moles. For the given reaction, delta Ng equal to sum of Ng of products minus sum of Ng of reactants, which is equal to 3 minus 2.5 moles. Delta Ng equal to 0.5 moles and delta U equal to minus 742.7 kilojoules per mole at T equal to 298 Kelvin. R equal to 8.314 10 to the power minus 3 kilojoules per mole per Kelvin. Substituting the values in the expression of delta H, we get delta H equal to minus 741.5 kilojoules per mole. Exercise 7. Calculate the enthalpy change on freezing of 1 mole of water at 10 degrees Celsius to ice at minus 10 degrees Celsius given delta fusion of H2O equal to 6.03 kilojoules per mole at 0 degrees Celsius if Cp equal to 75.3 per mole per Kelvin and Cp of water is 36.8 joules per mole per Kelvin. The solution is total enthalpy change involved in the transformation is the of the following changes. A. Energy change involved in the transformation of 1 mole of water at 10 degrees Celsius to 1 mole of water at 0 degrees Celsius. B. Energy change involved in the transformation of 1 mole of water at 0 degree to 1 mole of ice at 0 degrees Celsius. C. Energy change involved in the transformation of 1 mole of ice at 0 degrees Celsius to 1 mole of ice at minus 10 degrees Celsius. Therefore, delta H equal to Cp times H2OCl at delta T plus delta H2O fusion plus Cp H2O multiplied by delta T, which is equal to delta H equal to minus 7,533 per mole minus 6,030 joules per mole minus 368 joules per mole, which is equal to minus 7.151 kilojoules per mole. Therefore, the enthalpy change involved in the transformation is minus 7.151 kilojoules per mole. Exercise 8. For the chemical reaction given below, N2 plus 3H2 equal to 2NH3. If delta R of HO equal to minus 92.4 kilojoules per mole, what is the standard enthalpy of formation of ammonia, that is NH3 gas? Solution is standard of formation of a compound is the change in enthalpy that takes place during the formation of 1 mole of substance in its standard form from its constant elements in their standard state. Rewriting the given equation for 1 mole of ammonia, that is NH3 gas, we write half of N2 in gaseous state plus 3 by 2 of H2 in gaseous state gives 1 mole of NH3. Therefore, standard enthalpy of formation of NH3 in gaseous state equal to half of delta R of HO equal to half of minus 92.4 kilojoules per mole, which is equal to minus 46.2 kilojoules per mole. With this, we have reached the end of this session. Thank you for watching.